Welcome to the Extinction Level Event Podcast. I am your host, the Barrelman. This is episode 6. If you look on the actual list, you'll see that there's 4 episodes labeled. That's because one of them is not labeled as an episode number. It's labeled as an episode, but not an episode number. So there's really 5, even though there's only 4, and this is going to be episode 6. So I could either retitle those, and maybe I'll go back and do that, or just say it's really irrelevant what the number is. If you're listening, you're not listening because you're trying to be a completionist, or I don't know, maybe you are, but somehow I doubt that's the prevailing motivation. We're going to do just slightly different today, not completely different. It's mostly going to be the same, but slightly different in that I have a lot of notes all the time on things that I want to go over in the podcast, and so I want to basically kind of read through the notes. Some I'll read verbatim, some I'm just going to read as what it's meant as, whatever the chicken scratches I put on here. And then we'll go back over and talk about some topics, because I find that I start talking about stuff, go down some rabbit holes, expand and expound on things, and sometimes don't end up getting to everything. And some things don't even need like a huge explanation. Everything you really need to know is in the title, kind of a thing. So, like I said, we're going to go over this real quick. So the top, we have methane. In amounts, because that's something that's not talked about enough. Carbon dioxide is always kind of the star of the show. One of the main contributors, agriculture, potential release of massive methane in the Arctic, how global warming actually contributes to earthquakes. We have the earth cooling. We have the sun expansion. We have the rogue earth theory. We have the moon escaping from our orbit, and we have something I've looked up. I cannot see a name for this, so I'm giving it a name, even if the name is a bit contrary to the concept. But we can come up with that. It's not like some big important revelation or anything like, oh my God, we need to know that now. It's just something I've decided I'm going to start calling something, because nobody else has kind of coined a term for it. So I'm going to come up with something so that I can call it that from now on, and maybe nobody knows what I'm talking about, and maybe I have to explain it every time I say it. I don't know, but it's something, and I think it's nice to have something to just say blah blah and not have to just explain the whole thing every time. Such as like the Mandela effect. Like, if you don't know what the Mandela effect is, then that's not going to help you, right? But a lot of people know what the Mandela effect is, and therefore it keeps you from explaining the actual effect by just saying, oh, it's the Mandela effect, right? So let's get to some of this stuff. I'm kind of going to go a little bit no, we should really probably go just in order. It's just easier to just scroll down and know what we've talked about and what we haven't. So, and just I don't know how much I've edited out and not, but I do these recordings outside, so you might hear outside noises, birds and stuff, but this is kind of where I like to do my recording. It's nice, peaceful. I can watch nature while I'm doing it. So all right, so we're going to talk about methane. For the past 20 years, we pumped in 80% more methane into our atmosphere. This is a trend that's accelerating. Some of it's linear, but a lot of it's exponential. So, 80% of what we had before in the last 20 years. So then, add that plus another 10, 15% in another 20 years, right? So we're just huge amounts, and methane is way worse than carbon dioxide, right? So every bit of methane we're putting up is just way worse than all the carbon that we were putting up there. Not that it cancels out the carbon or anything. The carbon's still terrible. It's still a horrible thing, and yeah. So, but methane, it's worse, and we're pumping a ton of it in. We're looking at almost a doubling of the methane that we have there in the next 20 years. Methane being such a more potent greenhouse gas, and I don't know what the percentage is as far as how much more potent, but I believe the video suggested it was somewhere around 4 to 5 times more potent than the carbon dioxide because of how many hydrogen atoms were attached to the methane as opposed to the carbon dioxide. And of course, the chief creator of methane is agriculture, specifically animals, goats, sheep, cows, of course, being a huge, beef being one of the biggest industries, of course. And I'm not a vegan or a vegetarian. I like meat. I eat burgers. Burgers are one of my favorite things in the world. I don't really want to give up my burgers, but I also don't want to die. You know what I mean? So if I had to give up eating burgers so that we could all live and we all just kind of agreed to that, yeah, we'd figure something out. We'd make something else good. It wouldn't be the same, but, there's plenty of good things to eat in the world. But yeah, so I'm not saying this is somebody who hates hamburger and meat and beef and all that. And there's nothing like a good steak, right? But I also, again, like I said, I don't want to die for it. Agriculture, yeah, is a big problem for this. And yes, there are fixes. There aren't easy fixes, but just because it isn't easy doesn't mean it isn't worth doing. In fact, most things worth doing aren't easy. So what we have is a bunch of methane that's under an ice shelf. And as this ice shelf is melting, it's exposing a lot of this trapped methane. And there are scenarios in which the ice shelf just kind of, even if it doesn't 100% melt tomorrow, can still release most, if not all, of that methane in there. The amount of methane we are talking about is enough there that if it was released, it could increase the global temperature by 1 degree Celsius in a matter of months. Not years, not even a year, months. And they said a few months is about as accurate as they were willing to try to get, right? But still, a few months could raise the temperature a few degrees here on planet Earth. Again, it's Celsius. It's not Fahrenheit, so it's not actually 1 degree for those of my American audience thinking of that. So 1 degree Celsius in a few months. And of course, all this is going to have a snowballing effect. So it's not just, we'll just absorb the one. No, this is a contributing thing. It's just going to accelerate past that, right? This is just going to make it worse sooner, not just that's the 1 degree and then we're done kind of a thing. So we're going to have an increase in earthquakes. So why would climate change affect earthquakes? Well, it has to do with the heating and something that we had talked about on a previous podcast, which is actual ground temperature. Atomic cohesion has a lot to do with heat, with the energy in the system itself. So if you have a system that has a lot of energy in it, the atomic structures will start to break the bonds, right? That's why we have solids, which is, our Earth full of solids. And obviously there's water and stuff in there, but for the most part, when we think of the Earth, we think of rocks and sand and solid things. It takes solids and makes it into a liquid. So that's what's happening is those atomic bonds are breaking and it's becoming more, malleable and taking on the traits of a liquid because it's literally becoming a different state of matter. But it's not just a one-step process. It's not solid, liquid. The atoms being in a solidified structure just kind of stuck where they are. They're in particular forms. The crystals, you can easily see those lattices and structures, right? And rocks are the same way. And sometimes they're just kind of mishmashed in there, especially like obsidian. That's an amorphous structure, right? But it's still a solid structure. A solid structure doesn't just remain the way it is. Like, the solid structures can still have heat introduced, and they don't have to melt in order to change. So when those atomic structures start to weaken, what you have is changes in the characteristics of that solid. So what I mean is there are some points at which it could cool down again and become even stronger because now you've got a more solid crystalline matrix in there that's actually strengthened the bonds, right? But what we're talking about is while the energy is in there, you're breaking apart those bonds, even if you can re-solidify them even stronger. At this point, we haven't got to that. We're just at the bonds being broken. So even though you haven't moved a solid to a liquid, because again, it's a process, it's not just solid and then liquid, you're starting to heat these up, you're weakening the bonds. Even if they haven't broken yet, you're at least weakening the bonds, throwing a bunch of energy in. Energy in the form of heat in this case. So what's happening is the atomic structure, the material integrity of the rock and the stone and everything in there. Hi, Mr. Stellars J. Yeah, I know the peanuts are out. You ate them all. Sorry. More tomorrow. So the structural integrity starts to break down, and you get what was once a solid surface now starting to become a bit more malleable. Even if we're talking like diamond hard number 10, just going down to, number 9. I can't remember what mineral is at 9. I think there's at least one or two that are hardness 9. But the point is, we're still talking extremely hard material, right? But when you're talking about the plate tectonic forces, right? The geological forces here, where we can literally have the planet tear itself apart, tear holes right in the ground, right? Everybody's excited now. Bird's excited, the dog's excited. Where you can literally have the earth tear itself apart, regardless of how hard and solidified the rocks are, right? It'll still rip holes in it and slide along and just, tear this earth apart from the inside out, kind of a thing. So you don't even need malleability in these systems for quakes to happen, for these slides, in the plates to trigger these massive earthquakes. And we can get into the whole tsunami thing at another time. We're not getting to that right now. But the point is, you make those rocks just a little bit more malleable, and suddenly the stresses that are being placed on them and the solid surfaces that we once had that were keeping, say, the big one, right, from happening, all of a sudden, those aren't as strong as they are. They're not as resistant, which means we're going to have easier slippage. So we break down the structural integrity of the things that are basically holding back some of the more dangerous earthquakes, which would happen eventually anyways. It's not like, oh, we have this and they'll never happen. No, they're going to happen, but it's just when. And this could accelerate that. Now, we're not talking a direct, the earth heats up, therefore all the earthquakes happen kind of a thing. It's going to depend on the type of stone. It's going to depend on the location. It's going to obviously depend on how much heat energy that particular location gets, how easy it is to radiate out that heat. There's a lot of things involved. It's not just earth heats up, therefore earthquakes, huge thing. What I'm saying is it is definitely going to be a contributing factor. Climate change will definitely affect whether we have giant earthquakes or not, as far as timing goes, right? Do you have the big one in 100 years? Everybody says it's overdue, but the earth doesn't give a crap what you're saying. It doesn't care that you think it's overdue. If it wants to take another 100,000 years, it will. But will it take 100,000 years, or can we accelerate that and have it in 10? These are the kind of things that we can affect, right? And then not to say that it absolutely will happen and you can count on that. That's not what I'm saying. What I'm saying is it will have an effect. We can see that. And so some of these things, and proving whether it is or not, it would be extraordinarily difficult. Is it just time for this massive earthquake, or did the structural weakening of the stone and the rock actually have some sort of, bearing on when this exactly happened? Was the timetable accelerated? Proving that kind of thing would be extremely difficult. But as the heat permeates in, as we warm the globe in general, that's going to be a contributing factor, and it could set off some more disasters that a lot of people aren't even going to think about when it comes to something like climate change, right? Add to that, we have a quite different problem, right? So what we have is the Earth basically born of these smaller particles as they start to come together due to natural forces of gravity. And the gravity's influence starts to expand. And so more and more and more gets pulled into here, right? Until there really just isn't any particles, or they're being pulled on by other forces. Maybe strong solar winds come by, X flares or something that knocks some of them out. And so things we might have gathered, we haven't anymore. But the Earth starts to get large enough that starts to become round, which is one of the conditions of something being an official planet, right? Being roughly spherical. And we start getting to that point, and we now have tons and tons and tons of pressure from gravity pulling everything into this central point, because that's how gravity works. It radiates out in the sphere from a centralized point. Whatever the point would be, the greatest density and mass, right? Whatever has the greatest density and mass, that's the centralized point, and everything else radiates out from that, right? And everything has its own gravity, but those fields are going to be reinforcing with the other fields. So wherever you have the greatest concentration of fields, you're going to have the greatest center of gravity. So what's happening is that the Earth is got this, huge amount of pressure, and it is starting to liquefy all of this rock with this extreme heat. The early sun, brighter and hotter than before. Like, everything is basically contributing to us basically being a giant molten ball of rock now, not just a big solid surface. And I think it was like about 4.5 billion years ago, right, when the Earth was first being created, and we first can call it the Earth. That's at the point where we're basically just a giant molten ball. And it starts cooling from the outside in. Also, the material starts separating out. Heavier things sink, and lighter things, go towards the outside of the Earth. That's buoyancy, right? So we get all the big heavy metals. We get all the iron. Right, iron and nickel. That's what our core is made of. All that starts sinking into the center, and some of the lighter lithia or stone, right, starts expanding towards the outside and floats on it, kind of like a surface, a crust, if you will. Sorry, car went by. Birds are having a bit of a fit there. So you have all this primordial heat there that's in the Earth, but there isn't anything now creating that. We're not gaining any more notable mass. We're not being influenced by the sun enough to radiate heat all the way down into the core to any extent that it will be more than the heat exchange is naturally radiated, right? So the Earth is cooling at this point, and it's going to continue to cool for the rest of its existence. But what they're finding is there's these crystals. I can't remember what the crystals are called. There's something with a B. And that means that we are losing heat from our core quicker than we had thought that we were. Now, I don't know what the initial calculations on that. Nobody has ever really talked, at least in the schooling that I have ever taken in any science classes, about a timetable for the Earth cooling and losing its magnetosphere, and just, I guess maybe they thought that was too much of a downer, or maybe they thought it was such a distant thing that it's not even worth bringing up. Just like most people don't bring up the expansion of the sun unless they're talking about the sun specifically and its life cycle, and then they'll bring it up because it's kind of inevitable. You can't really talk about the life cycle of the sun and not mention that part, right? That's usually sorry, and that's usually when you start to hear about that. So we're finding out that the Earth is cooling quicker than we thought, which means that Earth is slowly becoming the new Mars. For more about that, we could do a separate podcast just about that. In obviously that would be a doomsday scenario, in which case the Earth would become much more like Mars. We would, obviously investigate all the mechanisms that would be happening and how soon things would happen in general and how long we would really have in a scenario like that. But it wouldn't be something where the Earth's core would be like, there's that movie, The Core, right, where the Earth's core stops spinning. It's not really going to do that. That's just not a part of physics where the Earth can just stop like that. The core can just stop spinning and you can restart it. It's a fun little movie. I actually kind of like the movie. It's not one of the greatest sci-fi movies of all time or anything, but I enjoyed it. It was fun. So I'm going to read you an excerpt that I found on just Googling it. They didn't give the exact source, but that's kind of how Google works sometimes when they give their little information at the very top to kind of give you what you're looking. I mean, it's nice and all, but that's kind of how it works. So it says, in a 2013 projection by Andrew Rushby of the University of East Anglia in the United Kingdom, pegged Earth's viability for life to be good for another 1.75 to 3.25 billion years, assuming there's no nuclear holocaust, rogue asteroid, or other unforeseen disaster. Yeah, I think the rest of that's kind of duh, but it was part of the quote, so I included it. So basically he's saying the viability of our planet, given how much quicker it's cooling, and when we will start to lose our magnetosphere and start to exist on what it will be an uninhabitable planet, is actually a lot quicker than we thought. We're obviously not talking tomorrow or your kids' generation or their kids or their great grand. Like, this is way, way down the line. Like, there will not be a human being left on this planet at that point, because we'll either be the next evolution or the next evolution after that. Billions of years. We're talking, eons of dominant species of the Earth having risen and fallen, right? I think it took about 1 billion years for single-celled proto-organisms to even come into a more complex form of life and start dominating the oceans, right? But that's not a one-step process, even though it's not a big leap to us, because it's like proto-organisms into finally, a fish. I actually know that's like a thing, right? There are still complexities that are being created in symbiosis that's being established and all of this stuff, right? So even though it took about 1 billion years to do all that, I believe, we're still talking a huge amount of evolution. And after that, once life became more complex, which obviously is the time we're in now, a more complex time, not the simpler time, life moved a lot faster, right? Obviously, the asteroid was one of the big things, but a lot of stuff has come out saying the dinosaurs were on their way out anyways. That the asteroid kind of kick-started the final nail in the coffin, but it wasn't the thing that killed the dinosaurs. The dinosaurs were on their way out. The asteroid just kind of accelerated that point. It really depends. We weren't there. It's hard to know, but that's a lot of prevailing theories nowadays. But the point is, they had their time. They were around for like 300 million years or something, and that's what, a third of a billion, right? And we're talking, earliest estimate is close to 2 billion, right? If we're just rounding, it's close to 2 billion, 1.75, but it's close to 2. So we're talking 1/6 of the time that's left for an entire species of animal to kind of rise to the dominant and then fall again without any human or other intelligent interactions, right? Just through evolution and survival and everything that happened. Obviously, the earth changing and doing different things and becoming different. The environment always changing just naturally because of the way the earth is. I think we're in a very stable period of the planet as far as a lot of these like geological events, giant moments where all the earth or all the volcanoes explode and pour in carbon dioxide. Yeah. I'm not saying anything about that can't happen, but I'm just saying I think we're in a much more stable geological point in the earth. The orbit, of course, will have a lot to do with things, and we do know that the earth is supposed to be moving into a new ice age. This is pre-climate change, right? That the earth is supposed to be moving into more of an ice age, and we're definitely disrupting that. And some people say, hey, good, we'll skip the ice age then. That's not, you don't do climate change to skip the ice age. All we do is just take it in a completely different disastrous direction. We don't avoid one. But so there we go. So that's a lot sooner, right, of a timetable now that we're looking at, though, than what we were looking at before. And before it was that the sun is about 5 billion years old. They expect it to live in its main sequence for 10 billion total. So that gives us about 5 billion years before the major expansion of the sun. The sun is supposed to go through a lot of little mini cycles before it goes through such a major expansion. So there will be, more radiation pouring from the sun at this point or that point, the solar cycles and all that. So it's not just when the sun expands, we're dead, but before that, we're perfectly fine. There will be times before that where we're not going to be perfectly fine, right? Okay, so then we get to my little coining of the phrase. So I've talked about this a lot in several episodes, and I looked it up to see if there was a phrase coined for this, and there wasn't that I could find. Maybe somebody can come up with it and say, hey, this is what it is. I don't know. But until then, I'm coining my own phrase. I'm not going to put my name on it. It's not a form of immortality. So I'm coining a phrase based on the scenario that if a giant asteroid was coming towards us and we had a few days left, maybe a week, that nobody would tell anybody anything because it's too late to do anything about it. And we don't want everybody just panicking for the last moments of their life. Let them enjoy their life. The asteroid's going to hit us anyways, whatever. You'll know it when it hits, right? So the origin being this asteroid theory is why I'm coining the phrase the way that I am, and the fact that they could keep something from us to keep us all from panicking, to keep us a little bit more docile, is something that could be applied to other things, not just the asteroid thing. But it doesn't matter because this is the origin, so this will still be applicable, even though they say that doesn't make sense because you're talking about an asteroid. Like, no, actually, we're just talking about the phenomenon, not necessarily just that specific scenario. Not that it should come up a lot, because it shouldn't, but, And then the other thing is we have this conspiracy theory asteroid that I promise we're going to get to in a minute or two. Well, maybe more than a minute or two, but we're definitely going to get to that conspiracy theory asteroid. And so what I wanted was to take the conspiracy theory asteroid and combine it with the asteroid scenario to come up with something for me to coin to say it's a this thing. And the thing I've decided is I'm going to call it the Apophis phenomenon. Right? I've looked up online. I looked up the scenario. I looked for anything that said also known as the blah blah effect or blah blah phenomenon or whatever it is. It's basically just a government cover-up of an impending and unavoidable disaster that they've decided to just let play out due to the fact that we can't do anything about it anyways. Now, if we can do something and they're just going to let us get wiped out because they just want us wiped out, so that they can like start over, whatever, evil genius plot villain style. That's different. This is, even if they wanted to stop it and tell people that they, you know, that they should do something to try to save themselves, they know there's no point because there's nothing that can be done. This is that scenario. And the fact that they just decided not to tell anybody that it's happening rather than to tell them it's happening and they can't do anything about it. So it's a specific type of scenario. There are different factors that if you shift it a little, it would be different. That's not this. And it's, like I said, I'm coining it the Apophis phenomenon is what I'm going to call it from now on, if I remember. And I probably won't. Really, what was that thing I called? Hopefully I keep it in my notes, right? So there is a theory about when the sun expands that one of the things that can happen is a rogue planet. The most likely scenario is that the Earth actually gets enveloped by the sun. There's also things that say that it's not even sure that the red giant sun will even reach us, right? That it might not even expand all the way out to our orbit. It doesn't matter if it hits us or not, we're fried, right? Just because you're not actually in the fire doesn't mean you're not close enough to the fire to be cooked, right? Put something on a spit, you rotate it over the fire, you don't put it in the fire, it's going to get plenty cooked. You don't need it right in the fire near its close, right? So even if it doesn't actually expand and envelop the Earth's done. It's not so we might not know. We're done. As soon as it starts getting into that phase, we're pretty much done without it even enveloping the Earth. So that, don't get your hopes on that one. But one of the theories is kind of a bit of a far out theory, but it is possible that instead the gravity, the shock wave, whatever it is, actually kicks us out of our orbit and we become a rogue planet. And that can end up being just as bad. It wouldn't be quite as instantaneous, but it would still be bad. There's a squirrel giving me a suspicious eye because he wants to go over and eat some peanuts. He sees that I'm here and talking, and he's wondering if I'm talking because I notice him. Go ahead, squirrel. I put the stuff out for everybody. That includes you. All right. There's also a lot of people know now, not everybody, that the moon... Oh, I guess I should start out with, what was it called? The moon something. It was the movie that came out not that long ago where the moon was crashing into the Earth. Well, that's not what's happening. The moon is slowly pulling away from the Earth, and it will leave at some point. But it's not supposed to leave. I was reading something on, I can't remember, I think it was Reddit, where somebody was talking about this. And I know I could just look up the numbers and find them, but I'm assuming this person knew what they were talking about because they were talking about these things and giving numbers. And they were talking about the sun expanding in about 5 billion years. They knew that. So they were saying that the moon is supposed to pull away in about 15 billion years. I don't know that exact number. I don't remember that from the last time I researched this. I do know that the moon pulling away from the Earth will happen after the sun expansion. So we're all going to get fried in the crispy critters long before we have to worry about the moon leaving. But it is on its way out. It's not on its way in. So there is that, because that is another doomsday scenario, the moon leaving. But unfortunately, due to physics and the way that our solar system works, that's not a scenario we even need to talk about because there just isn't a way for it to happen because of the timetable. And now, with the 5 billion years before the sun expands, that's not a problem for us either. That's another thing that we're not going to have to worry about. Now that we know that the Earth is cooling so much quicker than we thought, 1.75 billion to 3.25 is definitely sooner than 5 billion. Even at the latest, a 3.25, that's sooner than 5 billion, right? That's still way, way, way far in the future, of course. But that still gives us a range of roughly 2 to 3 billion years from now, right? Where the Earth is just going to stop being inhabitable because we're going to lose our magnetosphere. Now, What we're also going to do is we're going to talk about right now the conspiracy asteroid, which is, of course, Apophis, the one we were talking about. That's why I coined the Apophis phenomenon, right? So I have a few quotes here of information on Apophis. We don't need to, really go over the facts like a huge amount, but Apophis is about 1,100 feet or 335 meters across, which is not large enough to cause global extinction. However, it could wipe out a large city and cause planet-wide climate effects. So there we go for everybody who's worried about Apophis being a planet killer. It isn't. Now, if you happen to be anywhere near where it's going to hit, you're going to have a real bad day. But it is, in fact, not going to kill the planet. And in 2021, astronomers used radar observations and orbit analysis to determine that Apophis poses no risk of impacting Earth for at least 100 years. NASA's Center for Near-Earth Object Studies removed Apophis from this risk list. So that's really kind of where we are on that. And that's most of the stuff we want to get to. So I'm going to leave you here, and we'll come back for another episode on another day. Will we survive our own apocalypse? Only time will tell.